Hello, everyone. Welcome to the March edition of Ask Me Anything for the Mindscape podcast. I'm your host, John Carroll. And this, as you probably know, is the first version of the AMAs where the answers, this episode that we're listening to right now, is going to be released publicly. We haven't exactly figured out the best way to get it to the public. So for right now, it's just going to be the usual thing where I put it on the Patreon page and I'm just going to let it be accessible to the public. Most people won't know it because they don't visit the Patreon page, but I will let people know by Twitter or whatever when we eventually get a different system running, if that ever happens. The Patreon supporters method is not going to change in any way. You'll still get the episodes more or less as soon as they're recorded, more or less right here on the Patreon page. No ads or anything like that. Don't worry about it. Just so you know that whatever questions you ask, the answers I give will be sent out there to the world for everyone to listen to. Apologies that this is coming out a little bit later than usual. This is Sunday, March 8th when I'm recording this and releasing it. Of course, I was in Australia, did a very fun tour through Australia and New Zealand, sponsored by an organization called Think Inc., which is a wonderful little tiny organization that sends speakers dealing with fun intellectual topics around Australia and New Zealand. They're hoping to expand their purview to LA and California and elsewhere, so maybe you'll see them if you're in one of those areas soon. It was interesting when I flew into Australia, of course. People are careful now because we're fighting a virus, possible pandemic, the coronavirus and its associated infection, COVID-19, and the disease whose name I forget. The nomenclature is all complicated, but we all know what we mean. When you fly into New Zealand or Australia, they take this very seriously. There are questionnaires saying, have you been to mainland China in the last 14 days? Are you coughing? Do you have any symptoms of serious illness? When you fly back to the United States, it says, welcome back. There's really nothing at all that happens. Usually I'm not in favor of panicking or overreacting to things like this. But for those of us here in the US, I think that this is a situation where a little bit of reaction is absolutely called for. In some sense, it's a disease that has a low fatality rate, but it's a new disease we have no vaccine or cure for, and even a low fatality rate, if many, many people get it, is a terrible thing. You know, I've read credible estimates that the number of people in the world that will be infected by the virus is between 40% and 70% of the total world's population. So in a very real sense, you will probably be infected by this virus. Now, you can get infected and not get sick. And you can get sick and not die, especially if you're not already fighting with respiratory problems or elderly or frail or whatever. But still, this is something that I think makes perfect sense to worry about. I've already had several events that I was supposed to participate in be canceled. Many of you might know the March American Physical Society meeting was canceled literally the day before people were hopping on their planes. And I think I get it. I'm in favor of that. I think that if you can avoid unnecessary air travel, if you can avoid being in large groups of people, especially groups that are coming from all over the world in various different places, I certainly don't trust our current governmental setup here in the United States to do the right thing. They seem to be much more interested in keeping the reported numbers down than keeping the actual amount of infection low and dealing with it. They're not testing nearly as much as we could. So it makes sense to take some precautions by yourself, which of course includes more than anything else, washing your hands, right? Washing your hands and not going into danger zones are the two most obvious things that you can sensibly do. But, you don't need to completely cancel your life. You don't need to bunker down. I think that even domestic air travel for non-huge conference reasons is probably perfectly legitimate. Although, what do I know? I'm a physicist with a cat on his head in his Twitter bio, not a professional virologist or epidemiologist. With that, I think that we're ready to go. Some good questions this month, so let's go. First question is from Valkia, who says, in your talk at UBC from December, you mentioned that in a universe with emergent time and a finite dimensional Hilbert space, the number of possible states is finite, and so the universe must have a beginning and an end. Isn't it also possible that in such a universe there could be a closed loop of quantum states of some sort? Yeah, I think that's completely possible. I'm not even sure what the difference is, to be perfectly honest. In one of these universes, what we're imagining here is that quantum mechanics is living in a finite dimensional space of possibilities. So, as I will say, I think later on in the AMA, there's always an infinite number of quantum states in any Hilbert space, but the number of distinct quantum states, the number of quantum states with no overlap with each other, is a finite number in a finite dimensional Hilbert space. And the idea of emergent time in these models is that time is a label on the quantum states that is held by a clock that lives within the quantum states. So really, when you have these emergent time models with a finite dimensional Hilbert space, there's only a finite number of possible ticks of the clock because there are a finite number of distinct quantum states for the clock to have. But time is emergent in these models, so whether or not you think of the evolution as starting somewhere and ending somewhere versus going in a loop is kind of hard to distinguish what you mean, right? I mean, I think you can think of it in either way because time is not fundamental. Time is a way of thinking about interpreting these labels on the quantum states. Dmytro Shevchenko says, do you think logical absolutes, the laws of logic, law of excluded middle, stuff like that, are emergent rather than intrinsic to the universe? Could they be emergent from the wave function of the universe and the Schrödinger equation? This is, one of those subtle questions. I don't have a strong feeling about this, Dmytro. This is a question that relates to issues of mathematical Platonism in my mind. So Platonism is the idea that mathematical structures are real in some sense. My inclination is to not go that way, to not think of mathematical constructs as real, to think of the physical world as real. Whatever your attitude about this is, but I don't feel strongly about it, which is why I'm sort of speaking hesitatingly. Like, I've heard good arguments on either way, and I don't have a settled opinion my own. Whatever it is, whatever the reality level of a mathematical structure is, or a law of logic, it's a different kind of reality than tables and chairs or electrons or something like that. But I also don't think that they're emergent laws of mathematics and laws of logic. I think that they're descriptions, they're descriptions that you can't avoid. I think that's the difference that I would want to emphasize here. The laws of physics being emergent, the higher level laws of physics that are emergent, like fluid mechanics for fluids, for example, are contingent in the sense that in a different universe, you would have had different laws of physics. I don't think that the laws of logic or mathematics would be different in a different universe. They might not describe the universe, but I think that's a different thing. The laws of logic are the laws of logic. They follow from axioms to conclusions, and from different axioms you get to different conclusions. That's what math and logic do. What science does, trying to figure out which patterns actually describe our real contingent universe, is a different thing. So they're not emergent in the same way, just like they might not be real in the same way. Krabby Smales says, on the last AMA you state the broken egg, I've edited this a little bit just for length, but I think I got the essence correct. On the last AMA, you state the broken egg on the sidewalk is a record of a prior event, but only if we assume a low entropy boundary condition. Have you considered that a low entropy boundary condition may be part of what causal explanation is? What I mean is that causal explanation always consists in finding a compact, parsimonious description in terms of a combination of dynamic laws and boundary conditions. The most compact description of any present macrostate includes a low entropy boundary condition, which thus becomes the past. This is because lower entropy macrostates are also of lower algorithmic information content. If we derive a thermodynamic arrow in this way from parsimony, then we cannot also ask for an explanation of the low entropy early universe. Indeed, how could we justify any such theoretical explanation except by appeal to its parsimony? So I don't exactly agree with that. I think that there's some correct things going on here, but I think about it a little bit differently. So parenthetically, one thing to get clear, you say because lower entropy macrostates are also lower algorithmic information content. That's certainly not true as a general rule. The lowest algorithmic information content is in the highest entropy macrostate, right? The highest entropy macrostate is thermal equilibrium. It has essentially zero algorithmic information content. You just say, boom, thermal equilibrium. But likewise, some very, very low entropy macrostates also have low algorithmic information content. You say, all the gas is on one side of the box or something like that. There's no simple monotonic relationship between entropy and algorithmic information content. So that's one parenthetical remark. But the other one is, you say the most compact description of any present macrostate includes a low entropy boundary condition, which thus becomes the past. And I don't really agree with that one either. If you have a description of the present macrostate, its most compact description is just a statement of that present macrostate. If I say the gas is on one side of a box, that's it. That's the most compact description of that present macrostate. It may be true that the gas came from one tiny slice of the volume in the box at an earlier time, or it might be true that the gas used to be spread throughout the box and just through a random fluctuation, it moved all onto one side. Either one of those pasts is completely compatible with the present macrostate. The gas is on one half of the box. So you're adding extra stuff when you add a low entropy boundary condition to that description of the macrostate. So that's a feature of macrostates. That's if you have a good macro coarse graining, you describe current macrostates purely in terms of their present configuration. So adding a low entropy boundary condition is an extra piece of information, like it or not. In fact, it's an incredibly powerful extra piece of information, since in the space of all macrostates, in the space of all microstates corresponding to a certain present macrostate, the overwhelming majority of them will have come from a higher entropy past and go to a higher entropy future. So I really think that adding in the extra low entropy initial condition is not only extra, but it's a hugely leveraged extra bit of information. It's a tiny word, right? So it has low algorithmic information content. I agree with that. But it's far from necessary just to deal with the present macrostate. And it gives us an enormous amount of handle on what happened in the past. But it's extra. So I think that's why you sort of have to include it as an extra assumption, because without that assumption, you wouldn't be able to say the things we want to say about reconstructing things in the past from the present moment. John Hamill says, there are various conditions like certain brain injuries that prevent people from independently developing complex plans which project themselves into the future. People suffering from such conditions may be otherwise lucid and healthy. Why would it be wrong for me to push such people onto the truck going to the slaughterhouse to be killed in the same way as the cattle? So I think this is a very reasonable question to ask. Let me parenthetically, once again, editorialize a little bit. I know from having mentioned issues involving vegetarianism and eating meat and so forth in the past, these are highly emotionally charged issues, and I get that, and that's okay, right? It's not like a mistake to be emotionally invested in this. It's kind of a big deal. But my goal in this podcast and elsewhere in my life is to have as rational a conversation about these issues as we can, even when the issues are highly emotionally charged. These issues are hard. It's hard because moral philosophy is hard. So I think we have to respect the hardness of it all and not immediately go to the most emotionally charged language that we can find. Now, it's perfectly okay to say, I'm not in it for the rational discourse. I think I know what the rational answer is. I'm in it to change hearts and minds, right? To reach people at a visceral level, to be an activist, not an intellectual, and then by all means, then the emotionally resonant language makes perfect sense. But when you talk about putting people onto trucks going to slaughterhouses, you're not trying to have the most rational discussion you can. You're trying to make an emotional appeal. So I don't necessarily accuse you of doing this right now. I'm letting you know that this is how it appears to other people. And, again, if you just want to be an activist and convince people, that's fine. But I would be more in favor of trying to be as clear-eyed about it as you can. My mind about these issues is not at all made up. I'm very open to listening to different people's opinions and ideas about this, which is why I mentioned these things in my podcast conversations. Having said all that, I think that there's very often whenever anyone sort of tries to draw a line between here is what we can eat and here's what we can't eat, no matter where you draw the line, people will argue over where the line should be drawn, and that's a completely appropriate thing to do. In the case of those of us who think it's perfectly okay to eat meat, to eat animals, there's often, you try to explain why you treat animals differently than you treat human beings. And there's a move that is made that says, well, but some human beings are not going to fit into your line drawing as human beings. They're going to be on the other side because they have brain injuries or disabilities of some sort or another. I don't find these arguments in particular persuasive at all because I have no trouble whatsoever drawing the line at the species level rather than the individual level. If someone is a person, if someone is a human being, then I can treat them according to certain rules, whether or not they have the mental capacities of the typical human being. So I think that I have no trouble whatsoever, just as a simple answer to this question, saying, yes, it is wrong to push such people onto the truck going to the slaughterhouse. So that's the answer to the question. But of course, it brings up a lot of very, very interesting issues. When I was just in Australia, it was right at the time when the next person coming to Australia to do a tour with Think Inc. is Peter Singer, the very famous philosopher. And one of the, on the one hand, he is sort of the intellectual leader of the animal rights movement, right? He thinks that he's a vegetarian, he thinks that animals should not be killed, etc. But he's also, as a philosopher, tried to draw these lines very carefully rather than just, be emotional about it. And he's gotten in trouble because he is, one of the things that philosophers sometimes do is they have a set of moral intuitions and they try to build them up into a system. And then they say, well, I should believe what the system tells me. And sometimes when the system tells you something counterintuitive, you should say, well, maybe my system building wasn't very good. But other times you might want to say, I should believe in the system. So Singer is very good at believing in his own system. And sometimes it leads him to say things about the rights of disabled infants or mentally injured people that are not compatible with most people's moral intuitions. It's subtle, and I'm not going to be able to correctly state exactly what his position is, but let's just say it in that way. So people protested that he was going to come, and actually the venue in Auckland where he was supposed to speak canceled his engagement. They found another venue. I think it's a very bad idea to cancel an engagement like that. Like, whatever you might think about Peter Singer and his ideas, he's a super smart, intellectual, rational, world-leading philosopher. He is not some, activist for anything, anything inhuman or ugly or anything like that. He's exactly the kind of person who, if you disagree with, which is fine, you should be trying to persuade with reason and logic, not by canceling his speech. But anyway, that was a long digression. The point is, the fact that an individual human being is not capable of projecting themselves into the future, I get that. I would still want to protect their rights as a human being because they're a member of this species that does have that capability. But also, I think that most people, I'm not up on all the different levels of mental injuries that you can have here, brain injuries and so forth. But most people, even with the injuries that I'm aware of, are able to understand that they are being put on a truck going to a slaughterhouse, right? In a way that a cow is not. Of course, maybe you can argue that the cows are, they complain, etc. They probably, cows are able to have a little bit of anticipation of what's happening next. And I think that's a perfectly good argument to have, whether or not that is enough to put them in a different category. Okay, Rohit says, what do you think about the late Freeman Dyson's belief that there are more pressing matters than climate change, which may not statistically be that big a deal? Statically, you've written here, but I'm not sure what that means. But anyway, yeah, I think the late Freeman Dyson was completely wrong about climate change in many ways. Of course, the argument that there are more pressing matters may or may not be true. I'm a believer, as I talked about in the podcast with Martin Rees, that nuclear proliferation is a huge deal for us here on Earth. I have no real way of judging whether it's a more pressing matter than climate change, but I also have great belief in humanity's capability to handle more than one thing at once. In fact, I think it's kind of necessary. So the fact that there's a more pressing matter is completely irrelevant to me. I think that climate change is a hugely pressing matter and we should deal with it. So I think that Freeman Dyson was just wrong about that. Brad Wells says, would you please comment on the state of supersymmetry and by extension string theory, given the null results coming out of the Large Hadron Collider to date? My understanding is that most supersymmetry variants have strong correlation between the mass of at least some supersymmetric particles and the mass of the Higgs. Is this a deafening silence or just a work in progress? This is a great question. I think it's a very complicated complicated set of issues to do justice to. So on the one hand, it's very important to say that both string theory and supersymmetry don't automatically predict anything at the Large Hadron Collider. This is part of the problem with these models, is that they're frameworks and there's many, many specific ways to have models within them. And so it would have been great if we had found supersymmetric particles at the LHC. It would have had almost nothing to say about string theory. I mean, supersymmetry and string theory are different things. String theory predicts supersymmetry, but supersymmetry doesn't predict string theory. So it would have given, as a Bayesian, a tiny little boost to string theory if we had found supersymmetry at the LHC, but it's only a tiny little boost because you can absolutely have supersymmetry without string theory. Now, whether or not you should have expected supersymmetry at the LHC, I did write a blog post where I made my prediction ahead of time, but it's something like 50% that I personally predicted that you'd be able to find supersymmetry at the LHC. So I don't think it was very, very strong. There was a whole set of arguments, which I think were reasonable, that said, look, we have the Higgs boson. It's clearly at a mass scale much lower than what you would expect if you didn't know anything else. We have an explanation for how to explain that low mass scale, namely supersymmetry canceling out certain radiative corrections, certain quantum corrections to the mass of the Higgs. If that explanation is the right one, then you should find supersymmetric particles at the LHC. But of course, the reason why the Higgs boson has a low mass might have nothing to do with that particular supersymmetric solution to the hierarchy problem, as it's called, even if supersymmetry is still right. So if you didn't know about the Higgs boson and the hierarchy problem, if you were just doing supersymmetry, you wouldn't automatically say that the supersymmetric particles should be at the electroweak scale, where we could find them at the Large Hadron Collider, which, by the way, we might still, it might be that they're just around the corner, we haven't found them, but it's absolutely true that we could easily, in the space of all possible models, found them a long time ago. So I do personally think that the fact that we found... what I personally think is the fact that we've found nothing other than the Higgs boson so far is telling us an awful lot. Forget about supersymmetry. I mean, supersymmetry is a good idea, but it may or may not be true. But regardless of supersymmetry, it's still true that in our usual way of thinking, there is this weird unlikeliness that the Higgs boson would have the low mass that it does. That problem still arises. And not only supersymmetry, but sort of almost any easy, straightforward answer to that question predicts extra particles at the energies that are visible at the Large Hadron Collider, and we haven't found any of them. So that is absolutely saying something. Not only have we not found that, but we haven't found the dark matter particles that would have been an easy fit into supersymmetry or other weak scale theories. We still have the cosmological constant problem, etc. So I am very open to the idea that all of these little clues are telling us that there's something utterly wrong about our way of predicting what the masses of these particles should be, our way of distinguishing what is natural and what is not natural. Now, I know that some people say, well, we just shouldn't have made those predictions at all. We have no idea what's natural. I don't buy that either. I think that, physicists try to do the best they can. And until we have a better idea, we should go with what we have. So we have arguments that say that the low mass of the Higgs is not natural, and therefore we should try to explain it. Now, you can say those arguments are wrong, but I only am persuaded by you saying that if you have another reason to explain why the Higgs boson has the mass that it does. And those reasons are very hard to come by. I've tried myself. I've made zero progress. I've had some ideas. None of them panned out. So I hope that other people are taking seriously, and I think it's true, that other people are taking seriously the idea that the deafening silence at the LHC is a kind of a clue that a different approach is needed. That's easy to say. The hard part, of course, is to figure out what the different approach should be. There's an infinite number of potential different approaches one could take. Zachary Stopa says, why do scientists, when debating each other, when one person stops speaking, the other before the retort always begins with the word good? Do you guys know this is a thing? So I think it's a thing. Yeah, I think that we do know. I'm not sure if everyone does it. I know I do it, and I think, to be honest, I picked it up from David Albert, who was a philosopher. He's trained as a physicist, but he's a philosopher now. You probably have heard our podcast episode together, and David very famously and very obviously says good in that sort of way all the time. I think it's a good thing. I get why it's done. What you're doing is you're saying, we're having a logical, rational conversation. We're trying to first come to some agreement on things and then move forward. The word good signifies, okay, we've understood something now mutually. Let's move on to the next thing. So, I mean, maybe it's a verbal tick, but I think that there's much worse verbal ticks out there. Peter Gallay says, can you please comment on the recent discrepancies in determining the Hubble constant due to different methods of measuring the expansion rate of the universe? I don't have much comment on it. I am moving forward on the assumption that it will go away. I don't know that it will go away. I hope it doesn't go away. I hope that it's a huge deal and teaches us something really profound about the universe that we don't currently understand. But it's one of those cases where, again, as a good Bayesian, there's no easy explanation for. I should explain for those of you who are not following this discrepancy. There's something called the Hubble tension crisis. You can measure the Hubble constant, the rate of expansion of the universe, directly by looking at galaxies and supernovae nearby and seeing how far they are away and how fast they're moving away from us. There's also a kind of indirect way using the cosmic microwave background and the evolution of the asymmetries in temperature and so forth. These ways should give the same answer, and they give slightly discrepant answers. Exactly how big the discrepancy is a matter of debate, but it seems to be big enough that people are worried that these two methods are giving different answers. Again, I think it'll just go away because all of these methods are really, really hard, and it's easy to underestimate your systematic errors, and also because there's no obvious explanation for why that would be true. So, in 1998, when we found that the universe was accelerating rather than decelerating, a huge part of why that really remarkable and surprising result was so easy to accept was because we instantly had a theory that predicted it, right? The cosmological constant. And I think that's correctly taken in a Bayesian framework to be a good reason to give a certain experimental result extra credence. So I know that people are taking this result very seriously. As a researcher, you have to choose which results to take seriously and which not. My mode these days is to not be an ambulance chaser trying to explain the most recent tension in one or the other experimental result. My mode recently is to say, I'd rather take a step back. We have standard models in particle physics and cosmology and gravity. They're very, very good at fitting the data. They're not very good at fitting together. So I want to be more interested in the foundations of these subjects and figure out how to fit them together than try to figure out whether or not the most recent experimental result is actually telling us something. Frank Cockritz says, with regard to your and Max Tegmark's assigned probability of 50% to eternal inflation theory and its outcome of a multiverse, could you express your thoughts on just one possible alternative that would address the fine-tuning of constants of the universe in which we reside? So there's different kinds of things that people mean when you say fine-tuning. Sometimes you just mean the numbers are very different than what you might naively expect, like we already talked about with the Higgs boson mass or the vacuum energy. Sometimes you mean the fine-tuning that allows for the existence of life in the universe. So in either case, the most obvious alternative explanation is we got lucky. That's it. There is no explanation. This is just how the world is. We happen to live in a universe that allows for life to exist. There you go. All of these arguments about naturalness and so forth are not ever airtight, right? When you say that the values of the constants of nature are fine-tuned, that's not the same as saying that there is some disagreement between theory and experiment. That's just saying that if we randomly picked the constants of nature, given some measure on the space of all possible constants of nature, we would be surprised at these particular values. Who knows what that measure should be? And I don't think anyone thinks that we do randomly pick the constants of nature. So if it is what it is, that's an absolutely perfectly okay explanation for these things. The other thing, which I am always a big advocate of, is understanding that we don't know the conditions under which life can arise. If someone handed you the laws of physics and you didn't know about the periodic table and the nuclei and chemistry and life and whatever, you wouldn't be able to look at the standard model or the core theory laws of nature and say, oh yes, that allows for life, but if I change this parameter, it wouldn't, right? We are lucky enough to ex post facto know that the laws of physics that we actually have around us allow for life, but knowing whether or not other laws of physics would allow for life is an incredibly hard problem. So I am not at all confident that we can even say that the laws of physics are fine-tuned for life to exist. Anders says, imagine a cat in freefall with its back toward the ground. The cat will rotate itself to land on all fours. How does the cat do this without violating conservation of angular momentum? I read the official explanation, but I don't really understand it. So I'm sorry, Anders, this is just not the kind of physics I'm very good at. I'm self-aware enough to know that. There's a whole book by Greg Gabor about this and other sort of feline physics problems, if you're really interested in it. But even though I'm not going to be able to give you the complete answer, I will tell you the trick to understanding the answer, which is there's a difference between the idealizations that physicists use when understanding and talking about the universe and the real messy way the universe works. So sure, angular momentum is conserved for an isolated system. Cats falling down are not isolated systems. You know, they have different moments of inertia that interact in different ways with the air around them. It's never exactly true that they have zero angular momentum when you drop them. There's a lot of messy realities that come in between you and the simplified spherical cow explanation that we physicists will often give. So you should never be very surprised that the real world is a little bit more intricate and complicated than the world of physics explanations. Jake Johansson says, can you give me one of your classic style explanations on how we know that hidden variable theory is wrong? I'm not entirely sure that I fully grasp what I've read about it so far. So we don't know that hidden variable theory is wrong. Hidden variable theories could be right, also known as pilot wave theories or Bohmian mechanics or de Broglie-Bohm theory. These are versions of quantum mechanics that say that in addition to the wave function, there are extra variables that also tell us what we're going to observe once we actually do make a quantum observation. So the rough motto here is that the reason why, let's say in a double slit experiment, electrons sometimes appear particle-like and sometimes wave-like is because they are both. There really is a wave, the wave function, and there really is a particle, the electron, okay? So that could be right, you know, I don't know. I doubt it very much because, number one, most importantly, I just completely have no need for that, right? I think that the wave function alone provides exactly the same explanatory power, namely in the many worlds interpretation. So why in the world would I add extra variables on top of it? In these hidden variable theories, you still have a wave function. The wave function still obeys the Schrödinger equation. The wave function still represents part of reality. Then you add extra stuff on top of it to pick out one of the worlds that an Everettian would say that we live in. And I just don't see the need to actually do that. It is weird. Hidden variable theories is a weird theory because the wave function pushes around the particles, but the particles do not push around the wave function. If they did, it'd be experimentally rule-outable very, very quickly. And there's another reason why modern physicists don't give it a lot of credence, namely that it was developed, the hidden variable theories, in the context of non-relativistic quantum mechanics, where you have a particle with a position, etc. Of course, these days we use quantum field theory to describe the world. And if you care about gravity, there are those of us, including myself, who think that even quantum field theory is not up to the task and you have to look beyond that. And you need, so let's put it the charitable way. In these hidden variable theories, whenever you say, oh, it's not particles, it's fields, oh, it's not fields, it's something else, you have to start from scratch and figure out what the hidden variables are going to be, okay? I personally think that's going to be a really, really hard thing to do for quantum gravity, etc. Maybe impossible. Even for quantum field theory, people have done it. People have made progress in that direction, but it doesn't look pretty. It doesn't sort of naturally fall together. Whereas with many worlds in these different versions of the theory are just plug and play. You just have a Hamiltonian that makes the wave function move, and then your job is to interpret it correctly, and that's the job we're trying to do. James Kiddick says, I'm curious about the tools you use as a theoretical physicist, as well as your personal preferences. When doing theoretical work, how much of your time is spent in front of a piece of paper versus a whiteboard, chalkboard versus a computer? Do you geek out on writing instruments like specific brands of pencils or fountain pens or whatever? So I'm not a big geek about those things. Like, I get it. Some of my best friends care a lot about their writing implements and their chalk and so forth. When I actually do physics, 98% of it is me writing in one form or the other, not working at a computer. So, coding or doing numerical simulations is a tiny, tiny part, not zero, but a tiny part of my own working life. It has traditionally been pen. I don't really use pencils ever. My favorite pen, I do have a favorite kind of pen, but it's not like a fancy one. It's a cheapo Uniball Vision Elite. I love these pens, and I try to get them whenever I can, just so I have a big supply of them. But okay, I'm very happy to use whatever pen is around. I've been experimenting, as I think I've said, with using an iPad and an Apple Pencil. It's very, very good. There's a number of huge benefits of writing with the iPad and the Apple Pencil. Namely, that you can cut and paste, you can annotate PDFs, you can sign documents and things like that. There's also a pretty big downside, which is that the access time is just slow. Like if I have a 10-page long calculation and I'm writing on page 10 and I need a result that was on page 2, on paper it's trivial. You just look at it. On the iPad, you got to like scroll down and try to find it and then scroll back up and remember. So it's still not anywhere close to the convenience level of pen and paper for looking at previous pages or stuff like that. I do sometimes, very often, use a chalkboard or a whiteboard. I don't really care. I'm not a fanatic about that. Certainly when I'm talking to students or collaborators, we're standing in front of chalkboards or whiteboards all the time. Alexander Kabanov says, is the collective unconscious real in any useful sense of the word? So the collective unconscious, again, I'm not an expert on this, but it's a concept from Jungian psychology. I presume, since I'm not an expert, I'm just going to speak in vague generalities here. There's different ways to think about it, right? Like there's the idea that there is collective memory that is literally carried on by oral traditions and written traditions and handed down in different cultures share stories and mores and folkways and traditions, versus something a little bit more spooky, where there's sort of some non-verbal, non-literary transmission of information from minds of different generations to the others. My impression is that the Jungians or Jung himself was pretty spooky about this stuff. And to that extent, I think that it's not real at all. But there might be a more sort of metaphorical, allegorical sense in which the traditions that we hand down function as a collective unconscious in some way. I don't have a strong feeling about that. Thomas Prunty says, if I recall correctly in classical electromagnetics, you arbitrarily select an arrow of time by picking retarded potentials over advanced potentials. Is the situation different in quantum electrodynamics? How does that fit in with the entropy-driven arrow of time? It's not different in quantum electrodynamics at all. It's the same story. In my mind, it's exactly the same as the entropy-driven arrow of time. The fact that there are no electromagnetic waves that are focusing in on an oscillating electron. So, sorry, I should back up. For those of you who are not familiar with this story, if I shake an electron, spherical waves of electromagnetic radiation move away from that shaking electron. Light, that's where all the light comes from that is in your room right now. If the actual configuration of stuff in the universe was completely symmetric toward past and future, that means that when you shake an electron, there should be a set of spherically symmetric waves focusing in on it. But there are not, okay? That's a difference between the past and the future. And I think that's because of a low entropy boundary condition in the early universe. Because if it weren't for such a boundary condition, we'd be in thermal equilibrium, we'd be in electromagnetic equilibrium, there'd be exactly the same number of electromagnetic waves hitting the electron as leaving it. So to me, it's the same story. Not everyone agrees, but I think those people are wrong. Clyde Schechter says, on a few occasions you've said that if space is closed, then it is either a sphere or a torus. Are these the only possibilities or just examples? These are just examples. I'm sorry if I ever gave the misimpression that way. I will often say if space is closed like a sphere or a torus, because those are the closed manifolds that people are very well aware of. It is absolutely possible that space, that is the space of the whole universe we're talking about now, is closed, but is neither a sphere nor a torus. It's something more topologically complicated. There was a lot of excitement in the 1990s. There's a lot of interest experimentally in asking, could the universe be negatively curved and have a complicated finite topology, and could we actually observe that in the cosmic microwave background? I mean, roughly speaking, the answer is we've tried now, we've collected the data, and it's not there. We see no evidence observationally for that topology, but it could just be larger than the observable universe. That's completely a possibility. Philip Myman says, my question is about zero amplitudes and near zero amplitudes. Do zero, presumably this is the amplitude of a quantum mechanical wave function, a specific possibility within it, do zero amplitude events still happen but with width zero, or do they not happen in a fundamentally different way from simply happening with smaller and smaller width? Yeah, I think they don't happen. There's no such thing as happening with zero width. That's a difference. I think that's a fundamentally different thing. There are things in the wave function for which there can be zero amplitude, and you say that those things don't happen. Now, you might argue that, in the real world, if there's a continuous possibility of amplitudes, the chances that you will get exactly zero are very small, but there's sort of counter arguments to that. Like, as my favorite example is always, there's zero amplitude for a quantum transition between two different states with different electric charge. Okay, we say the technical term there is that there are super selection sectors for electrical charge. But if you want to say, like, if you have a spin that is a spin up and spin down, can you truly, really, absolutely get it into a situation where the amplitude for observing spin down is exactly zero? That might be harder to do. But conditionally, counterfactually, if you did, then yes, it would just not happen. It doesn't happen with zero. Brendan Hall says, do you believe in the circularity of language and definitions? Do you believe that the circularity of language and definitions is a true problem for philosophy? I'm reminded of your conversation with Philip Goff, where he seemed to invoke the problem of circular definitions to justify intrinsic natures. Do you feel a similar urge to solve a problem of definitions like Philip does? I think if I understood that discussion that we had correctly, that Philip is worried about the fact that, you have things like mass and force and physics, but you can't define perfectly well any one of those concepts without also defining the others, right? And you define them in terms of each other. I do not think that's a problem at all. I think that, as I think I said in that conversation, what I think you do is you have a mathematical formalism that you call your theory of physics, and there are some axioms, some definitions, and things do absolutely, relate to each other within that formalism. And then you say that that maps onto the world. And I am kind of a coherentist when it comes to truth, so I think that it's important that your system fit together, that all your definitions be mutually sensible, but that's not really a problem. I don't think that there's any grounding. Like, I think that as I discuss in the big picture, this is a philosophical difference between different kinds of people. I'm someone who doesn't think that there needs to be an absolutely firm foundation that you can't question, and then you build everything on top of that foundation. There is a bottom, in my mind, a bottom level set of laws of physics, even though we don't know what they are, but our knowledge of the laws of physics is not foundational on anything. It's always contingent. It's always like, well, this is the best we can do. We're trying to fit in everything we understand logically and mathematically with all of the empirical data that we have. And I think that's fine. I don't think it's really a problem at all. In fact, I think it's sort of inevitable. There's really no other way to do it. Santiago Torres says, what does physics have to say about how we should think about the concept of causation? Is it correct to say that we should not apply the concept of cause beyond the limits of our experience to describe any fundamental aspect of reality? Well, I wouldn't say the limits of our experience. I think the concept of cause is, as some of you know from my previous discussions, a higher level emergent phenomenon. So when you stub your toe and it hurts, you are absolutely within your rights to say, my toe hurts because I stubbed it, because I banged it against the table, okay? There's nothing wrong with that. You're not making a mistake when you do that. But that kind of language, which makes perfect sense in the macroscopic world of our experience, ceases making sense at the microscopic level, or even the sort of pristine level of Newtonian mechanics, where you don't have entropy, you don't have an arrow of time, you just have very simple systems obeying reversible, deterministic laws of physics. In those senses, in those cases where you have deterministic reversible laws, the usual notion of cause and effect ceases to have its usual oomph, right? It's not that anything goes, it's that it's replaced by a set of laws, by a set of patterns, usually differential equations. So there's still a way of describing the relationship between the situation of the world at one moment of time and another moment of time, but that description is not in terms of cause and effect, it's in terms of the laws of physics. Gerard Driven says, okay, sitting in a room, atom clock on the floor and one at the ceiling. The one at the ceiling where there is less gravity ticks faster. With my not good developed physics mind, I call it excitement for now. Is there a limit to this excitement? Presumably that's the fastness of the ticking. The speed of oscillating of the atom from being in a gravity field to a place where there is no gravity field. So I think this is going to come up. Yeah, this is the very next question that's going to come up also. Let me ask the next question and answer them both together. The next question is from David Lang, who says, special relativity tells us the faster we move in space, the slower our clock runs in time, and it's symmetrical. The world's fastest man, Usain Bolt, goes through the slowest time according to his cesium stopwatch. I've edited this for length a little bit. His watch would show even less time than the official timekeeper because it was in motion. He set the record for greatest time dilation by a human on foot at 100 meters. He has earned the right to be called the world's slowest man through time. So let me just say a few things that I think are true about relativity and time that are relevant to both of these questions, Gerard's and David's. I would really be reluctant to ever say that clocks tick faster or slower. Because if you were there with the clock, you would always see it ticking at 1 second per second. What else could you possibly see it ticking at? Because all of the clocks, including your mental clocks and your perception, would be affected by gravity or by your velocity in exactly the same way. So there is a rate at which clocks tick, 1 second per second. And to Gerard's question, yes, there is something called zero gravitational field, flat space. We can come very, very close to that, far away from any gravitating bodies, and clocks would tick at 1 second per second. The only thing you can do is talk about the relative amount of total ticks that a clock feels. And if you're really precise about it, if you really want to get it right, you can only compare what the clocks are doing when they are literally right next to each other at the same point in space. When two clocks are separated, you need to send a signal back and forth to see what they're doing. And different ways of sending that signal will get you different answers. So the really rigorous, well-defined way of doing this is to start clocks at the same part of space-time, send them on different trajectories, and then bring them back together like you do in the twin paradox. This is exactly the condition under which you will say the clock that was in a less gravitational field had more ticks to it than one that you sent down onto the Earth or near the black hole and came back, okay? But you're very tempted to say, therefore, the clock that was in the gravitational field must have been ticking more slowly. I would advocate not saying that. Or you might want to say the clock that was carried by Usain Bolt was ticking more slowly. I would advocate not saying that. Usain Bolt's cesium wristwatch was still ticking at 1 second per second. It's only the comparison when he's done running in which the whole journey was different, okay? So this is why I like to use this analogy of walking, like space rather than space-time. You can walk between 2 points on a straight line, and that will be the minimum distance you can possibly traverse. You can also walk on a curved path between those 2 points, and if you carry an odometer with you, your odometer will say you have walked more steps, more distance, even though you went from the same point to the same point. How is it possible that you went more distance? Well, I mean, no one is surprised by that, right? The ticking clocks are exactly the same way, except that you always go through less time rather than more distance. So don't think of clocks ticking faster or slower. Think of taking a shortcut through time. If you either travel near the speed of light and go out and come back, or you spend a lot of time in a gravitational field, you get to the future event faster experiencing fewer ticks of the clock than you would if you had just stayed out there away from gravity, moving at zero velocity. Cyclopropane says, I loved your interview with Kwame Anthony Appiah. Thank you. I like that one too. The more you touch on our global identities versus our smaller, pettier nationalistic identities, the more I enjoyed it. At what point do you think nations, governments, cultures are able to shed their guilt for past atrocities? How can I live in the USA as a first-generation citizen and not acknowledge that my success here is based on the shoulders of slaves and the genocide of Native Americans? So I think that there's a little bit of a collision here between two different concepts. You say, at what point can you shed guilt, and at what point do you acknowledge that your success is based on past misdeeds? And I think these are two different things. Guilt and acknowledgement are very different things. I'm all in favor of acknowledging, and I'm also in favor of shedding guilt, but those are two different processes. You should never stop acknowledging. Like, I don't think there's any point at which you said, okay, sorry, I did something wrong, but therefore you stop saying that you've done something wrong or admitting that you've done something wrong. Typically, whether it's the United States or Germany or Japan or anywhere else, because most cultures have bad things in their past, typically the error is on the other side, right? A reluctance to admit that you've done something wrong in the past. It's not that you are over-correcting for what you've done in the past. So I think it's good to admit and acknowledge the truth of history, that there have been terrible things done in the past, and some of us have benefited from those terrible things. That doesn't mean you should personally feel guilty. I don't think that a person should feel guilty for what their ancestors did. I think they should acknowledge what their ancestors did and admit the truth of it and understand that. And I'm much more interested in trying to make the present conditions fair and equitable than in feeling bad or feeling good. I don't think you should feel a special pride in what your ancestors did either. You don't get either pride or guilt for that. You are not around, right? You should acknowledge the truth of what they've done and try to make the present world as good and equitable and fair as you can. Kirk Briggs said, I like the philosophy of Schopenhauer a lot. At the same time, I recognize that he is a total pig when speaking about women. How do you reconcile it? Do I let his inappropriate attitudes influence my opinion of his philosophy? I think that I wouldn't advocate letting the personal failings of people influence your attitude about their creations, about their works, right? To the extent that their works are independent of their personal foibles. Because guess what? Everybody has personal foibles, okay? This is why I'm not in favor of having heroes or hero worshiping. I think that people do good things, and you should give them credit for the good things they do without making them your hero, because there might be bad things that they've done, or there might not. But when we're talking about public figures or historical figures, we rarely know them personally, right? We rarely know who they are. We rarely know how they treat people who are on a lower level of status and power than them. Maybe they're very sweet, adorable people. Maybe they're not. But you don't know. I don't know. And so I'm not going to say that they're my hero or role model. I will say that they have done something good, and I will admire that. And, in terms of accomplishments in philosophy or science, I think that there's all sorts of awful people who've done really wonderful philosophy and science, and we should give them credit for their good philosophy and science. It becomes a much harder question in my mind when it's art, when it's literature or painting or music rather than philosophy or science, because the enjoyment that we have of those things is much more subjective, right? Isaac Newton may have been a terrible person. He was a terrible person in many ways. That has zero impact on the efficacy of Newton's laws. But, if you watched Nanette by Hannah Gadsby, and she makes a good case that Picasso does not deserve your admiration, I think it's hard to argue that Picasso's paintings were really good. But when we learn about what a terrible person he was, does that color our enjoyment of the paintings? And I think, yeah, there's nothing wrong with that. Since our enjoyment of the paintings is purely subjective, of course, objective things like the identity and the nature of the artist can affect your enjoyment of them. I'm not saying that it necessarily should affect your enjoyment of it because it's subjective. You can make that choice for yourself, but I think it's completely legitimate to let it affect your enjoyment of them. Dan O'Neill says, what if it were your job to go back in time, sit down with Isaac Newton, and explain general relativity to him? How difficult would it be, and what do you imagine it would be like? Well, I hope this for Isaac would not be upset that I just said he was a terrible person in many ways. I'd like to think it wouldn't be that difficult. I mean, it would be difficult in the sense that there's a lot that Isaac Newton doesn't know compared to what we know now. I mean, not just general relativity, but tensor calculus, for that matter, vector calculus, right? There's a lot of things that we are teaching our physics students in their first year as undergraduates that Isaac Newton never heard of. So there's an enormous amount of background that you would have to teach Isaac, but he was very smart. So I think that you have an easier time teaching it to him. I have zero idea of how open-minded he was to these new ideas. My guess is that he would catch up very, very quickly. We are not intrinsically smarter than people from a few hundred years ago. We just know a lot more. And I think that he would still be someone who qualifies as a physics genius, even if you went back and tried to teach him modern physics. Graham Henry says, can black holes be viewed as objects that convert mass energy into space-time curvature? Does this mean that mass energy space-time can be viewed as a single thing? So I don't think that there's any such conversion process going on. It's a weird way that we talk about black holes because black holes are weird. They're outside our everyday experience. And as I've said many times on this podcast, the singularity of a black hole is not a point at the middle. It is a moment of time in the future. Later on, we're going to get to the Big Bang, which was a moment of time in the past. We visualize these things as points, but they're really not. They're really moments. So we will often say matter falls into a black hole and goes and hits the singularity. And that's true, but it's also true that the matter is still there. The matter is inside the black hole, and it is moving toward the future, and in the future, in some very short period of time, typically, it will hit the singularity. But while we're outside the black hole, the matter is still inside, the matter that went into making that black hole. So it didn't get converted into space-time curvature. There's a relationship, an interplay between matter and space-time that led to a black hole. Robert Ruxandrescu says, imagine that Laplace's demon exists and knows the position and momentum of every particle in the universe. So we're being Newtonian for the moment. Would it be able to predict that I didn't like a particular ice cream or that I was sad 3 days ago and how sad I was? In other words, would it be able to grasp the quality of my qualia based on just easy problem properties? So I think it's a little bit of an undefined question, but I think we can we can fix it up a little bit. The point is, what do you mean by Laplace's demon? So Laplace himself had this view of a vast intelligence that knew the position and velocity of every particle and could therefore predict the future and the past of every particle. But the question is, does Laplace's demon know anything else, right? So in some sense, there's a minimal version of Laplace's demon where literally the only thing this vast intelligence knows are the positions and velocities of particles. It doesn't know that there are things called words or chairs or planets. It just knows a long list of particles and their positions, like if it were literally a computer with a data file, right? A computer with a data file can do a simulation of a supernova blowing up. But if you asked it in words, how hot was the supernova, it would have no idea. You could write a subprogram, though, right? You could easily add to your program an extra little routine that said, calculate the temperature, and it would be able to do that. So in the point of view of myself or anyone else who is a physicalist about consciousness, you could easily imagine a version of Laplace's demon that did have access to these quality questions, to what we think of as our qualia. Is this collection of atoms a person? Is this person sad or happy? Are they experiencing red, etc.? For someone like me, all of those supervene on the physical locations of the particles and therefore are in principle calculable by a Laplace's demon level intelligence from that information. But you have to tell me whether or not you've actually given the demon the calculational capacity and the right definitions to actually answer those questions. Joshua Levine says, have you ever tried psychedelics? If so, do you think that they can have any true value for helping you see things in new ways? So we mentioned this a little bit in my recent podcast with Robin Carhart-Harris, the effects that psychedelics have. I have tried them once in my life. I tried LSD. The story is told in Jennifer Willett, my wife's book called Me, Myself, and Why. I was not there I was mostly there for moral support and to sort of be the caregiver and, making sure everything went wrong. So I was not sort of giving myself over to the psychedelic experience in a complete way. So I am in no way claiming that I really have tried all different psychedelics and tried them in the appropriate ways and so forth. I am someone who believes that on the one hand, psychedelics can be very, very helpful in helping people get out of addictions or ruts or depressions or things like that. They can help people with pain management. They can help people face end-of-life crises kind of things. I'm a big believer in the therapeutic value of psychedelics. Your question is, do they have any true value for helping you see things in new ways? Well, I don't know what exactly that means, right? Like I did just to amuse myself when I did the LSD trip. I said, does this help me with the physics problems that I was working on at the time, the physics research problems? The answer to that was certainly no. Like it was much harder to write down equations and solve them when you were on LSD than when you were not. Probably not a surprise. I think that it's very plausible to me that being on psychedelics might lead you to some sort of creative breakthrough by seeing things in a different way. I don't think it gives you any deep insight that is over and above what you in principle could get without them, right? It might help ease you get there, but everything that is in principle figure-outable on psychedelics, I would argue is in principle figure-outable without them. Stefan Berniger says, how does general relativity impact the electromagnetic force? More specifically, how are electromagnetic waves, atoms, molecules, crystals, and ultimately macroscopic objects held together by electromagnetic forces reacting to vibrating space-time? So I don't think I wouldn't use the phrase vibrating space-time. I would say curved space-time. If an object like the Earth is more or less static, then the space-time around it is more or less static, but it is curved by the Earth having its energy and momentum just sitting there. I think that the short answer to your question is the whole point of general relativity is that gravity is universal, that gravity couples to and interacts with everything in exactly the same way. This was what led Einstein to the great insight that we should treat gravity not as a force moving through space-time, but as a feature of space-time itself, as the curvature of space-time. So to the best of our current understanding of physics, everything, whether it's electromagnetism or ordinary matter particles like electrons and protons or other forces like the strong nuclear force, feel exactly the same gravitational force. They feel the same curvature of space-time. So certainly gravity both affects electromagnetism and is affected by electromagnetism because electromagnetic forces have energy and momentum just like everything else. Liam Appleba says, you've mentioned that we don't know if the dimensionality of Hilbert space is finite or infinite. If it were infinite, do we know if it's countably infinite or uncountably infinite? I don't think we know that. I can certainly say that the simple examples that we use in textbooks and so forth, where the dimension where Hilbert space is infinite, I think it's safe to say it's uncountably infinite. But this actually, it turns out to be a really, really tricky question. Like, take just the simple harmonic oscillator. This is everyone's simplest possible quantum system. Okay, so a ball attached to a spring where there's an equilibrium where it can just stay stationary, or you can move it away from the equilibrium and it will oscillate back and forth. There's a quantum version of that. And the question of whether or not a vector space is countably infinite or uncountably infinite can be thought of in terms of what is the basis for that vector space and how many basis elements does it have, a countably infinite number or an uncountably infinite number. In the most straightforward way of thinking about the simple harmonic oscillator, you can write it down in a basis which is uncountably infinite. The position basis, is it located at x1 or x2 or x3? But there's another basis, the energy level basis, which is discrete and countable. I should, by the way, say for those who don't know these words, different versions of infinity exist. Georg Cantor showed this back in the 19th century. Countable means a notion of infinity which looks like the integers, right? From -1, -2, -3, 0, 1, 2, 3, the counting numbers and their negative numbers. This is a countable infinity. What Cantor showed is that the continuum, the real numbers from -infinity to infinity, has strictly greater set of numbers in it than the integers does. So, and they're called uncountable because you can't count them. There you go. We don't know is the short answer. And even in simple examples, you could imagine the answer going either way. So I'm not sure. There are certainly people out there who understand this level of mathematical nicety within quantum mechanics way better than I do. So you could look that up on Wikipedia probably. More likely than I would. Is a simple harmonic oscillator an example of a countably infinite or uncountably infinite Hilbert space? Once you get to quantum field theory, it's pretty clearly uncountably infinite because even the classical theory has uncountably infinite states, just like the harmonic oscillator does. So anyway, short answer is no, we don't know, I don't know. I could see it going either way. Scott S. says, in the book Powering the Future, Robert Laughlin says that we have two broad choices with respect to nuclear power. There's enough uranium on Earth to either 1, provide electricity for about 200 years via a process that does not lead to radioactive elements that can be used in nuclear weapons, or 2, essentially provide electricity for thousands of years, but the byproducts can be weaponized. He does not discuss thorium reactors. Do you know enough about the subject to comment, or can you suggest a resource for further information? No, I do not know enough about this to comment. I will say the tiny little bit that I have to say about this is I'm quite optimistic about non-nuclear power for the long term, solar power especially, batteries will get better, etc. Whether or not nuclear power is very, very useful in the short term, I'm very open-minded about. Traditionally I was very pro-nuclear power, but I certainly admit there are many, many details that I'm not an expert on. Martin Rees, who knows more about it than I do, was very pro-nuclear power in our conversation. But 200 years sounds to me like enough time to figure out other sources of power, and I'm extremely worried about weaponizing nuclear fuel and nuclear reaction products. Therefore, at my current state of very primitive knowledge, I'd be much in favor of processes for nuclear power that did not lead to radioactive elements that could be weaponized. Marian Marcali says, I was thinking of recent experiments which seem to conclude that most animals have an innate number sense and can even do some basic math. Doesn't this hint at a starting point for a more formal universal communication between us and other species? I don't think so. Again, I'm not an expert on this, but I don't think that the problems that we have communicating with other species are because we don't have a common language. I just don't think that's the problem at all. I think that our thoughts are just very different intrinsically, right? This is super obvious when it comes to most animals, right? When you try to talk to an ant or a cat, we can't teach them a language that will let them chat with us. They just don't have the capacity to do that. For much smarter animals, for other primates or dolphins or octopuses or whatever, I still don't think that the problem is we don't have a language. I think that they don't have the capacity for language that we do. I mean, they do have some capacity, even dogs and cats have some capacity for understanding things we say and for communicating to us with sounds that they make. But there are levels that they cannot reach, right? That is why human beings are a little bit different. I've never heard any animals be trained to use the subjunctive mood in a grammatically proper way, for example. So I don't really think it's a language that is holding us back. Ron Jacobson says, is it workable to approach many worlds by postulating that the universal wave function is a superposition of all possible worlds, and that whenever we make a quantum measurement, we simply gain some information that narrows down which world we happen to live in? Yeah, I think this is a viable way of thinking about many worlds as far as I know. So I'll rephrase the suggestion as, instead of saying we are in one big world that then splits and differentiates as different subsystems become entangled with each other, is it okay to imagine there are many worlds to start, but all the worlds to start are identical. And then what happens is they simply become different, but all the number of worlds are already there from the start. People have absolutely looked into this. Can you do it that way? There are arguments back and forth. I kind of don't care. I don't think it's a crucially important distinction, honestly. Like, my attitude toward the worlds is that they are a human convenience. What really exists is the wave function of the universe, and all else is commentary, right? So what I would do to rephrase that question is, are we allowed to talk about quantum mechanics by subdividing it into different worlds from the start, or do the worlds have to be subdivided later? It's certainly more natural for me to imagine subdividing into separate worlds after the individual experiments are done and quantum systems become entangled with their environments, because it's only then that the worlds are distinguishable and they can't interact with each other, etc. Right? To me, that's what makes the worlds a sensible concept. But there are other ways of talking about it, and that's fine with me. That does not violate any of my deeply held principles. Sandro Stuckey says, my question is about the black hole information puzzle. Where does the randomness in black hole radiation come from? And then I edit a little bit, but he goes on to say, in Hawking's calculation, black hole radiation seems not to be deterministic. It's truly random, even without any branching. How is that compatible with the many worlds interpretation, which seems to be a deterministic theory? Is this a defect of Hawking's calculation or of the many worlds interpretation? Well, I think this is exactly the black hole radiation paradox or puzzle, whatever you want to call it. The point is that Hawking's calculation does not seem to follow the rules of quantum mechanics. It does not seem to start so to be very clear here to anyone who's not been following, in quantum mechanics, we start with a wave function of the universe. In the many worlds theory, we have an equation, the generalized version of the Schrödinger equation for whatever situation you're interested in, that shows us how that wave function evolves, and it's completely deterministic. In many worlds, that wave function involves more and more worlds branching toward the future, but the overall wave function is still deterministic. Hawking's calculation says that that single wave function evolves into not a superposition, but a mixture of many different wave functions. The technical term is a mixed state or a density matrix or a density operator rather than a single pure wave function. So that is not what many worlds says. That is a conflict with many worlds. The question is it a defect of Hawking's calculation? Probably. That's what most of us believe, right? We think that, he made some assumptions that don't hold true in the real world, and we're trying to fix them. That is the black hole information puzzle. How do you fix them? Turns out to be really, really difficult to fix them, but that's what we're trying to do. And, the jury is not completely in on whether or not it's fixable, and many worlds is a perfectly good description of that, or whether black holes are truly information destroying, which would be the other alternative. Bryce Graham says, in the Q&A after your brief history of quantum mechanics talk, you mentioned that while writing Something Deeply Hidden, you made 50 quantum spin measurements for an example. You admitted that in some universe you would have measured them all spin up. You seem to have shrugged it off like it wasn't a big deal and would have just thought someone broke the machine. Does that mean that in some branch of the universe there is a poor physicist who has only and will only ever measure spin up? So yes, that means exactly that. And I talk about this in the book. And again, I think that this is going to come up again later in the AMA. So let me explain the attitude that I think one should have toward this. If you believed in a version of quantum mechanics that was truly stochastic, that one in which there was a chance that you would measure 20 spins in a row or 50 spins in a row and get all spin up, but it was a small chance, that wouldn't bother you, right? You think that there's more likely things that are more typical, less likely things that are less typical. If you're going to believe many worlds at all, you have to understand that there is a similar attitude toward those things in many worlds. It is true that all the universes become true, but there are way more where you get the likely outcomes than the ones in which you get the unlikely outcomes. So the probabilities work out exactly the same way. The fact that there is an extremely, extremely low probability universe that really exists, but one in which the outcomes of the experiments will be statistically unlikely, is fine. You can't guarantee that every experimenter is always going to get the right answers. That's just a feature of statistics. I think that some people have a tendency in many worlds to say, well, look, all the worlds are real, and I'm going to implicitly treat them as equally real, treat them as equally important. But the very, very low amplitude worlds should be treated as less important, even though they are real. That's the only way that many worlds is ever going to make sense. Petros Pisius says, when a photon is detected after a double-slit experiment, how many new worlds are being created? I'm not exactly sure what this refers to. I'm not sure what role the double slit has here. If you fire a photon through a screen, whether or not it goes through double slits, it will hit the screen at some point. And in the typical way of thinking about things, where you have an infinite number of positions where the atoms on the screen could be, and an infinite number of positions where the photon could hit it, there are an infinite number of worlds that the universe breaks into. But of course, once you have an infinity like that, you shouldn't be counting the worlds. What you can do is you can talk about the relative number of worlds with certain properties versus other properties. So what we talk about is the relative number of worlds where the photon hit in this particular location on the screen, this particular non-zero area sized box of the screen. You sort of coarse grain it and you say, what is the probability? What is the fraction of worlds that's where the photon landed? Those are the kinds of things you can talk about when you have a continuum of possibilities. It's better to think of it as a continuum of possibilities than as literally an infinite number of worlds, even though the words work out the same way. Vampiricon says, have you ever watched the Avatar cartoon? And the answer is no, I haven't. So I have no wise things to say about that. Barry Wallace says, Kirk or Picard. I have watched Star Trek, and I think I'm going to say Picard here. I like both. I like old Star Trek, which I grew up with, even though it was already in reruns when I started watching it. But I think as captains go, I would rather have Jean-Luc on my side than James T. Kirk. He just seems like a little bit more of a level-headed guy. Simon Carter says, what was your opinion of Freeman Dyson, and do you think his stance on climate change impacted his reputation? I think there's no doubt that Freeman Dyson was an incredibly good and creative and technically proficient physicist. He arguably deserved to share the Nobel Prize. He helped understand the renormalization of infinities in quantum electrodynamics. The prize went to Feynman and Schwinger and Tominaga, and there's a limit, right? You're only allowed to give the Nobel Prize to 3 people, but Dyson certainly would have been perfectly understandable as a choice along with those folks. And he did a whole bunch of other things. He worked on the Oklo natural reactor, for example, this thing in Africa where there was a naturally occurring nuclear chain reaction, which we can use to put limits on the change in the values of physical constants over time. Has his stance on climate change impacted his reputation? Well, I think that, his stance on climate change was damaging. It's more damaging to the cause of doing something about climate change when a clearly brilliant, famous, accomplished scientist says we don't need to worry about it than someone who is just off the street. So I think that it bothered people that he made such a big deal about it. But I don't think it affected his reputation as a physicist. I think that his ability to do calculations in quantum electrodynamics was just as good as it ever was. Peter Sue says, in context of the famous double-slit experiment, when done with light of sufficient intensity, it's my understanding that you can compute the shape of the interference pattern in 2 ways. First, as a classical interference between electromagnetic waves, and then also as an interference pattern between the probability amplitudes of the quantum wave function. Presumably somewhere there's an example of someone doing this calculation both ways and showing they get the right answer. This is interesting because a priori one has no reason to believe that electromagnetic waves are at all related to complex probability amplitudes. Well, I think that's not exactly right. I'm not sure about the phrase a priori here because, nothing here is a priori at all. You're developing a theory and seeing whether it works. But the point is there absolutely is a relationship between complex probability amplitudes and electromagnetic waves. The classical wave that you get in classical electromagnetism emerges out of the quantum electrodynamic description. And the way it emerges is that areas in which the electric and magnetic fields are large correspond to large number of photons that would be observed, which correspond to a large probability amplitude for observing a bunch of photons. So I think, in fact, that the relationship between them is pretty straightforward. And indeed, you do get the same answer in that limit of a large occupation number of photons. Justin Bailey says, you said previously that the existence of the universe is a brute fact that you accept. That's hard for me. Old as it is, I think the first mover argument is hard to refute. How do you respond to that argument? I think it's super duper easy to refute the first mover argument. I mean, the whole point of arguments that are similar to the first mover argument, everything that moves needs a mover, blah, 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 therefore there's a first mover, is to deny the very first premise. It's not true that everything that moves needs a mover. I mean, we've known that for 1,000 years since we first started to understand conservation of momentum. When you were an Aristotelian physicist, you look around the world and notice that in order to get things moving, you have to push them. But we know better now. There's a thing called conservation of inertia, conservation of momentum. The natural thing is for things to be moving. And so there does not need to be any explanation for why things move. And I think that, the universe is the same way. But in particular, even if it weren't, it's not at all clear that things that apply to things in the universe necessarily apply to the universe as a whole. So I think that the right question to ask in the modern era where we know about science is not what caused or what created or what brought into motion the universe, but what are the laws of physics that allow the universe to exist? And you can then ask yourself, are there laws of physics that can describe the universe and its existence in a perfectly self-contained, consistent, internally coherent way? And from everything we know, the answer is yes. We don't know completely what those laws are yet, so we might be wrong about that, but we have every reason to believe that such laws exist. You don't need to imagine there's anything outside the universe to bring it into existence. Humberto Nani says, besides that we can only move to the future, what other facts of our universe make it look like we're inside a black hole? I don't think that there's any facts about our universe that make it look like the inside of a black hole. I am on record as saying, please do not think that the universe looks like the inside of a black hole. Black holes are things that exist in otherwise empty space, where there's a region of space with an event horizon around them with the property that things can come into the event horizon and join us in the region, but they can't go out. That's what a black hole is. That is not what our universe is, as far as we know, at all. If anything, our universe is kind of like the time reverse of a black hole. It's kind of like a white hole, where there is a singularity in the past rather than the future. But even then, it's not exactly like that. It's the universe. It's a different thing than a black hole. Gregor Anilak says, how much time do you spend on these Ask Me Anything episodes? Do you prepare the answers or do you go with the flow live? So I think what I generally do is I try to go into the Patreon post. I cut and paste all the questions into a separate text document. Then I go through all the questions and I try to edit them down a little bit. Some folks tend to go on a little bit in their question asking, which is fine, but not everyone else listening necessarily wants to hear the entire question. So I try to edit them down to the essence of it. And while I'm doing that, I will think a little bit about what answer I'm going to give. And then once that editing is done, I can go in and actually answer them in real time. The editing and the thinking about answers will take a couple of hours, 2 or 3 hours typically, and then the recording also takes 2 or 3 hours typically. I always aspire to just go through in one fell swoop and do all the questions. It rarely happens. Either my voice goes out or something like that. So over the course of an afternoon on the weekend, I can usually get it done. Paul Torek says, here's a scenario to explore the ideas of downward causation and mixing levels of explanation. A crystallographer uses a very narrow X-ray beam to analyze the microscopic shifts in metals that have been subjected to stress. She takes an aluminum automotive part manufactured by a new process and analyzes the particular 90-degree elbow at which these parts typically fall. She rotates the part just so and places it in the analyzer. She subjects the part to a certain cycle of stresses, then rotates the part to the same orientation and places the elbow in the same position with sub-millimeter accuracy. Her macroscopic actions determine which microscopic crystals are subjected to X-rays and which aren't. Why doesn't this explanation count as mixing levels or downward causation? So there's two reasons why I don't think it counts as downward causation. It does in some sense count as mixing levels just because the macroscopic level gives us a description of the world which is necessarily incomplete. If you have a description of the world where there's no such things as atoms, where there are pieces of metal and there are, machines and things like that, you can deal with them, then you can use that description to describe what happens only up to the point where your description doesn't need to require any reference to atoms. If you use your macroscopic world to observe atoms and then you take actions on the basis of what you've observed, then your purely macroscopic description does not suffice to explain exactly what happened. So you can aid it, you can abet it, augment it, I guess is the word I'm looking for here. You can augment it, which is what we do in the real world, by using a macroscopic description that also dips into a microscopic description when necessary and then goes back to the macroscopic description. And that's perfectly fine. There's nothing wrong with that. But alternatively, you could completely describe things at the microscopic level. You don't need to refer to a crystallographer or a machine or anything. You could just refer to what the atoms are doing, and you would get the right answer. If you had Laplace's demon level of specificity about what was going on, you would say exactly what was happening without any reference to what was happening at the higher level whatsoever. That's why downward causation is not necessary for these to understand these actions. Andre Mirabelli says, what criteria do you support for determining which recurrent process should be used as the standard good clock to determine whether one time interval has the same duration as a subsequent one so that competing fundamental theories can be fairly adjudicated? I don't really have any dog in this fight, as we say. This is a technological question about what makes the best clocks, right? Some frequency of some atomic transition or nuclear transition or something like that. That is way more specific and technological than anything that I'm an expert in. Sorry about that. Gregory Kusnik says, what's on the chalkboard behind you in your Patreon profile picture? That was a picture taken at Caltech. So it's a chalkboard at Caltech with some Lagrangians for quantum field theories behind me, or maybe some actions or something like that. But anyway, some equations for quantum field theory. I don't remember the specific ones. In fact, I didn't write them. They were there already when we just took the picture. It was in a public area, not in my office. Ramon Rocha says, do you enjoy stories about the paranormal or supernatural? And have you ever personally experienced something very strange that you couldn't rationally explain? So I enjoy all sorts of stories about things that I don't think are true. I mean, I'm a big fan of the Marvel movies for that matter. Have I personally experienced anything that I can't rationally explain? Sure, there's plenty of things that I can't explain. I think what you're getting at is, are there things which I think do not have a rational explanation? And for there, the answer is no. I think that, again, like a good Bayesian, we know enough about the laws of physics and how they work and how successful they are to think that whenever something happens, I'm going to put a very, very, very high credence in a completely physicalist, naturalist, rational explanation. It would have to be a very, very blatant and unmistakable violation of the laws of physics before I started shifting my credences to something supernatural or paranormal. Sandeep Chitale says, presumably the Big Bang started from a single point. One point can only be arranged one way. One microstate equals one macrostate. Therefore, it's the lowest entropy. Why is that not right? So it's not right for a few reasons. The Big Bang did not start from a single point. It started, well, it depends on what you mean, right? The Big Bang in classical general relativity is a point at which the curvature of space-time is infinitely big, and therefore that point is not described by classical general relativity. So you simply cannot say anything about it. What you should do is sort of imagine cutting off that point, stopping your description just before you get there, and then what you have is space and time immediately after the Big Bang, and space itself could be infinitely big in extent. There's no limit to how big space could be. So therefore, there's no reason whatsoever for it to be a single point or just in one microstate or one macrostate. And it's more specific than that, right? The Big Bang is not a point. Even if you cheat and add it back in to the description, the Big Bang is a moment of time. It is a moment that before which there are no other moments, if that is indeed the description that is true for the real universe, which we don't know. You can verify all of this by thinking about the Big Bang in reverse, right? Thinking about a big crunch. If you let a whole bunch of matter and energy crunch in a contracting universe instead of expanding as we think that our past actually did, there's absolutely no reason for the universe to smooth out as it crunches together. All of the things that we know about the laws of physics predict that it would get lumpier and lumpier. The higher entropy states are extremely inhomogeneous and lumpy as you approach that singularity. That's how we know that the real Big Bang, whatever it was that created a universe that was extremely smooth, was much, much lower entropy than it needed to be. James O'Sullivan says, in the double slit experiment, why does the electron's interaction with the slits not cause decoherence? Are the slits themselves not already entangled with the environment, or is it because the slits don't interact with electromagnetic radiation? Well, you have to be a little bit careful here. I mean, the double slit experiment is an idealization. For real slits, they might very well become entangled with the electron going through if you're not too careful. But in the idealization of the typical traditional double slit experiment, you're imagining that the state of the double slits, the state of the barrier through which the electrons are trying to pass, is completely unaffected by the electron. Therefore, there is no entanglement generated between the electron and the slits, right? And therefore, decoherence is not going to happen. Decoherence is always the entanglement between the quantum system you're looking at and the wider environment. If the slits are not affected, then there's nothing there entangling the electron. Aldo Mendez Martins says, could the fact that from the perspective of a photon the universe seems to be frozen in time be the reason why in the delayed choice two slit experiment the photons interfere with all photons past and present? Could it be that all photons exist at the same time but in different positions in space? So you have to distinguish between the time that is read by a clock moving along some trajectory versus the time as seen from the outside. When people say that photons experience no time, this is just a way of saying that the literal space-time interval along a light-like trajectory is zero. What it would be more accurate to say is that there just is no clock that can pass along, that can be carried along by a photon. It's not like the photon is experiencing no time. It's that time is not something that the photon could experience, if that's a sensible distinction to make. But of course, we have time passing as the photon passes by us. There's absolutely no problem with assigning a time of each point in the photon's trajectory. It's just the time that we use as a coordinate, not the time that the photon is experiencing. So I would say there's no truth to the idea that all photons, past, present, and future, are interfering or interacting with each other in any way. According to the laws of physics as we understand them, things only interact when they are at the same moment of time. Lineo Miziara says, is the block universe an unescapable consequence of special relativity, or can we conjecture an alternative view of time apart from the B theory of time? So the B theory of time refers to this idea that there really is a block universe. The A theory in this nomenclature that was put forward by McTaggart years ago, the A theory is one in which the present moment exists and sort of it marches forward in time. So most physicists are B theorists. They believe that all time is equally real to the extent that they care, which is not very much. And one of the arguments put forward is, of course, special relativity. In special relativity, there's no preferred way to slice the universe into moments of time. Different observers will do it differently. So how in the world could what is real depend on how a single observer chooses to slice the universe into different moments of time? So is that an escapable argument? You know, almost all arguments are escapable. I don't want to say it's an unescapable consequence. This is a philosophical perspective, right? It's not really a prediction that is made by some physical theory. So I think that there definitely, as an empirical matter, are people in the world who perfectly accept special relativity and yet do not accept the block universe. So there you go. It must not be an unescapable consequence. But also, you know, I think that on the flip side of that, I believe that the block universe is perfectly sensible and would be even without special relativity. I think the simple fact of conservation of information and the fact that what you know at one moment of time is enough to predict the past, present, and future is enough to convince me that the block universe is a good perspective to bring to these kinds of questions. Anon, an anonymous questioner, says, physics outsiders hear a lot of non-established theories, but it's hard to separate out what's probable and what's speculative. What are your rapid-fire, unjustified, not really thinking credences for these hypotheses being true? Are there any propositions where your personal credences differ from most of the physics establishment? So there's a long list of propositions that I'm being asked for credences for. So I've edited it down a little bit, but most of them are still here. So is dark matter made of WIMPs? I would have said 80% chance, but we haven't found them, and the LHC hasn't found anything, so now I'm down to about 50% chance. More than 1% of dark matter interacts with itself with dark forces. I think that's very unlikely, maybe 5% chance or 10% chance that that's true, something like that. It's conceivable. I would love it. I'm the author of various theories along those lines, but I don't see any real strong evidence for it yet. Axions exist. I think that's axions are a good idea. I might put them at a 30 or 40% chance of being real. Magnetic monopoles exist. I think that there's very, very tiny credence that a magnetic monopole exists that we might find in our observable universe, but it's possible that magnetic monopoles are conceivable according to the laws of physics that might actually govern our universe. I just don't think that we have any lying around. Tachyons exist, I think, is a negligible credence, way less than 1%. Neutrinos have mass and travel at less than the speed of light. I think that's true, 99% plus. Photons have mass and travel at the speed of light. I think that's false, less than 1%. Supersymmetry, something like supersymmetry at some energy, we don't know where it is. I would put, I think that's probably likely. It's one of those things that, just seems to make everything nicer if it exists. So maybe 60 or 70% credence on that. The standard model has something really wrong with it that we've already discovered, but just don't realize it. I think that's unlikely right now, so that's less than 10% chance for me. Same as above for GR, less than 2% chance. Will have replaced the standard model in my lifetime. That's a tough one. That's one where I don't even trust my own credences because I really, really, really want it to be true that we will have superseded the standard model in my lifetime. But we don't seem to be right there. We don't seem to be on the verge or the cusp of it happening. So I will put a 40% credence that we'll have done it. But that might be overly optimistic or pessimistic. It's just very hard to tell. Jeffrey Irving says, what's your credence that we can do an infinite amount of useful contribution in our future light cone? I expect this to be low but not zero, and I'm curious as to where your main non-zero term would come from. I'm going to apologize because I don't know exactly how to turn this into an operationally well-defined question. I don't know what an infinite amount of useful contribution would really be. I mean, it depends on useful. It depends on what sort of measure we use to measure the amount of usefulness and things like that. I will say that I think that the simplest version of what we currently understand about cosmology predicts that the universe will equilibrate and reach maximum entropy in some finite time. And so the smart money is on a finite amount of anything existing in our future light cone, any influence we might have. But, we don't know. So I think that there's some non-zero credence on any other possibility. So, I can't give a very specific answer to where the main non-zero term would come from because I'm not quite sure what I'm being asked to imagine. Sorry about that. Abdul Afzal says, if you were to organize Moving Naturalism Forward 2.0 sometime this year, which 5 people would you like to participate in the conference? So I'm gonna punt on this one a little bit because I don't like to answer questions like this because, I might do it, right? I might actually organize a conference, but I haven't done it. And I haven't decided what kinds of person I would invite to something like that. So I don't want to sort of say out loud who I would invite and then end up not inviting them. Does that make sense? Does that make sense to you? But I think that you can get an idea of some people who I think would be good by looking at former guests of the Mindscape podcast and asking yourself, which of these people are the kinds that might do well at a conference on naturalism. I think that someone like Patricia Churchland, I can mention out loud because she was actually invited to the first Moving Naturalism Forward conference and couldn't make it just because of personal reasons that time. But there's a bunch of people among the guests who, have thoughtful ideas about how the universe works at a deep level and how we can connect those to ideas about morality and living in the universe and consciousness and the origin of life, all of these big questions that naturalists have to face up to. So play the game the other way. Make up your own Moving Naturalism Forward conference out of pre-existing guests from the Mindscape podcast. George Clune says, Many cosmologists believe that inflationary cosmology is the best way to describe the very early universe. However, I think that in a previous podcast you said it was probably not right. What are the main arguments against this idea, and what is the best competing theory? So I don't think I said it's probably not right. I think that inflation is one of those things which I put 50% credence on. Inflation is really good at certain things. What it's good at will be different when you listen to different people giving you the sales pitch for it. I definitely have a minority point of view on this because I take the entropy of the early universe problem very, very seriously, and inflation makes that problem worse. Inflation makes the early universe sensible by positing an even lower entropy initial condition than the conventional Big Bang model does. So that's why I don't think that it's anywhere near close to a sufficient answer to why the early universe looks the way it does. But it might be part of a more comprehensive answer. You know, in the paper that I wrote with Jennifer Chen years ago, 15 years ago now, about the multiverse and the arrow of time, we absolutely used inflation as a crucial element in our theory. There's another paper I wrote with Lisa Randall and Matt Johnson about changing the number of dimensions dynamically, where again, inflation would play an important role in connecting a theory like that to reality. So I'm all in favor of inflation in that sense. What I really think inflation does is it gives you leverage for inventing theories where the initial conditions of our universe are set at the Planck scale, at the Planck distance. The physical size of our universe might only be 1 Planck length across, and inflation could help explain how it expands up to the universe we see. Whereas in conventional hot Big Bang cosmology, at the moment when the curvature and density was at the Planck scale, the physical size of our observable universe was more like a centimeter across, which is some crazily humongous length scale for particle physics to try to explain. So in some sense, inflation gives you an attractive, easy target. That's the good news. The bad news is it requires extra fine-tuning to make it happen, and we don't really have a compelling mechanism for which it really did happen. We have many mechanisms. We don't have any way of choosing between the different possibilities. Rick Coyote says, if neutrinos are so multitudinous, why are they so hard to detect? It seems to me that they're just sheer numbers would have the detectors going off constantly. So I think that you're not thinking about this hard enough, Rick. Of course, for any one detector, there will be a probability that if a neutrino goes through it, the detector will go off, okay? Because neutrinos are very weakly interacting, that probability is a small number. So you take that probability times the number of neutrinos passing through to get the total number that you expect to see in any one run of your experiment. No matter how many neutrinos there are, I can invent a probability that any one of them will be detected that is so small that the expected number of neutrinos you see is 0 or very, very close to 0. Is much, much less than 1, let's put it that way. So this is a case where you just have to write down the equation, right? You can't just sort of intuit it off your head. There's always an interaction that is so weak that no matter how many particles there are, you will not observe them. Victor Alejandro Weiner says, I have a silly question this time around. Do you know Sean B. Carroll? Have you read his books on Evo Devo, evolution and development? I do know my evil twin, Sean B. Carroll. He's a couple of years older than me, but he has the beard, so that's how you know he's the evil twin. He is one of the very few people I will happily admit is a future target for the Mindscape podcast. He writes great books about evolution and development. I highly recommend them. Paul Hess says, many worlds is often described by talking about worlds existing with all possible choices being made. But why? Do we believe, for any good reason, that Sean's free will is due to random quantum processes instead of just being dependent on classical but currently unknown states and brain mechanisms relating to the state of his brain, such as his mood, etc.? Well, Paul, I recommend that you buy a book that I've seen on sale called Something Deeply Hidden, which talks about exactly this kind of thing in great detail. And that book will go to great lengths to tell you that there is no relationship whatsoever between the many worlds interpretation of quantum mechanics and choices being made by human beings. There's just no relationship at all, one way or the other. It's not that making choices causes world to branch. It's not that worlds branching causes choices to be made. These are two separate things. And indeed, I agree with you. I think that for the most part, the workings of the brain are perfectly classical, but we just don't know the specific microscopic states. That's what gives us uncertainty about what decisions are going to be made, not anything to do with quantum mechanics. Zane Jacob says, I'm a master's student in applied math, doing research in scientific machine learning, and recently I've been thinking about how to do effective reduced order modeling when you don't have good intuition for the underlying dynamics. This relates pretty naturally to the problem of coarse-graining quantum mechanics. So my question is essentially, how should one go about finding an effective coarse graining when you really have no idea what exactly you're looking for? I think this is a really good question, actually, and I think that it's one that has been under-addressed in the literature, in part because people don't take many worlds seriously enough. Ashmeet Singh, who is a student at Caltech, he and I have been trying to develop what we call mad dog Everettianism, where not only do you have the many worlds interpretation of quantum mechanics, but you don't assume any structure pre-existing that gives you a classical handle on the wave function. You have to get that structure to emerge out of it. And so there's good ideas from other people about how locality and spatial positions can emerge. We wrote one paper, Ashmeet and I, on how you could use principal component analysis to get a coarse graining where you didn't know much about the quantum dynamics. But I think that there's a paper we're writing right now which is much more relevant to the question you're asking on what we call quantum mereology. That's the question of how you divide divide wholes into parts. That's what mereology is, the relationship between wholes and parts. So to an Everettian, where you think that the whole world is described by a single wave function, if that's all you know is the wave function and the Hamiltonian that tells you how it evolves, then the mechanism to go from there to a certain way of characterizing the wave function so that you can coarse grain it is highly non-trivial. It has to do with entropy, you'll be unsurprised to learn, and it has to do with emergence, and it has to do with the existence of effective higher level descriptions which require just an incomplete amount of information. Basically what you want to do is look for the factorization into system and environment so that the system states have as much classical behavior as they can, while the minimum amount of entanglement growth between the system and its environment. So this is what you need to look like an emergent, coarse-grained, higher-level classical world. But making that operational, I think there's still a lot of work to be done in that, so I don't think there's any final answers quite yet. Maxim Alexandrovitz says, my question is regarding quantum computers. Let's say it will soon be possible to create a very accurate model of a small part of the universe, for example, our moon. What would be the discretization level of such a model? As far as I understand, with traditional computers, there's always a limit in which you could say, aha, you missed part of the simulation because of the discretization. Could such a model be indistinguishable from our real moon, a quantum model, even on subatomic particle level, and therefore could it be a real world inside a real world? So I'm not exactly sure what you're saying, but I think I understand. You know, even though there are a finite number of qubits in a quantum computer, as we said, because Hilbert space is a vector space, there's always an infinite number of quantum states that could be described by that set of qubits, unlike a truly classical set of bits where there's only a finite number of ones and zeros, right? A single qubit has an infinite number of possible states because you can add any linear combination of spin up and spin down, for example. However, that is not enough to model something like the moon, which has a lot of particles. To correctly model something like the moon without any loss of information due to discretization or something equivalent to discretization would require a Hilbert space as large as the Hilbert space of the moon. So roughly speaking, you would need a quantum computer as large as the moon. And then you're not really computing the moon, you're just simulating it. You're just making a copy of it. Paulina Barron says, I'm interested in what your stand is on universal basic income. So I'm in favor of it. I think it's a great idea. You know, I'm someone who believes that you help people out by giving them money. Right? I'm not someone who believes that you're cheating people out of the chance of getting dignity by not giving them money and insisting that they work. You know, working is good for some people. It's drudgery and bad for other people. Income is good for just about everybody. So I'm in favor of doing it. I've done no careful research into the feasibility or the best way to get there or anything like that. So I think it's a wonderful goal to have, something to work toward. I'm not exactly sure what the best route to getting there really is. Charles Hertz says, suppose that there were a civilization on another planet whose science and technology were for all practical purposes identical to ours in 2020. Suppose that the inhabitants were aware through astronomy of the existence of our Earth and for whatever reason set about to look intensively for signs of intelligent life there. Can you give me a ballpark estimate of how far away their planet could be and still leave them with a decent chance of success? No, I really can't. That sounds like a homework problem that I would have to sit down and do some calculations for. Presumably it could be done, but it depends not only on what we are beaming out into the universe, but the sensitivity of the radio telescopes that they would be using to look for us, etc. So it's a doable problem, but one that I don't really have the time to sit down and do. I do think that it brings up this related fact that looking for intelligent civilizations by scanning the sky in radio telescopes is something that I personally think is incredibly unlikely to ever work, because I think that the chances for another civilization in our state of technological capability to be right there at the right time is extremely low. And once a civilization gets to a higher level of technological capability, they're not going to wastefully beam out radio waves into the surrounding space for no good reason. So I think that there's better ways to look for technological civilizations elsewhere. Patrick Freeney says the controversy about the Hubble constant being either 69.7 kilometers per second per megaparsec versus 73.5 rages on. Given that two different methods are being used for the calculation, why is it so important that there's a small discrepancy between them that is labeled a cosmic crisis? So I talked about this a little bit earlier on, but look, I don't label it a cosmic crisis. I think there's a certain amount of marketing that is going on in labeling it a cosmic crisis. It would be a cosmic opportunity if it were true, because it would be telling us something really important about the universe. But, to be fair, let's put it on the other side. The two methods should agree. Right? I mean, just because you use two methods, if you're measuring the same thing and you believe in an external reality, you're supposed to get the same answer. So either something's really going on or one of the methods is wrong. It's not that because they're two methods, they're measuring different things. So one way or the other, there's something to be figured out that we haven't quite figured out yet. Michael McCready says, I struggle with the idea that the Big Bang occurred everywhere, and that regardless of where you find yourself in the universe, you would essentially observe the same cosmic surroundings. Why, if you found yourself on the expanding edge of the universe, would you not see an empty night sky in the direction of that edge? So the answer here is that there's no such thing as the expanding edge of the universe. There's the expanding edge of what we can see from here, but if you were there, then what we can see from here would be irrelevant. We would be on the edge as far as you're concerned, and we're not sure what you would see if you looked in the other direction, but the easiest, most natural, most likely thing to imagine is that it's similar to what we see in the universe where we do observe in our current universe. In other words, that things are more or less uniform from the perspective of someone who is far away, 10 billion or 20 billion light years away, just as they are to us right here, right now. There's no edge to the universe. There's no sensible cosmological model in which the universe has anything like a real edge. It could be infinite, or it could be finite. It could be homogeneous and isotropic, or it could be very, very different. But there's no reason to think it has an edge. Jose Ignacio Alcantara, says, I very much agree with your approach that if we are to develop a quantum theory of gravity, it makes much more sense to look for it arising from a quantum origin than a classical one. But to my mind, there's a hiccup. What if quantum theory turns out not to be a fundamental description of fundamental reality? To this end, I was hoping that you might invite Lee Smolin for one of your podcasts soon. So, it's always possible that quantum theory is not a fundamental description of reality. But as I said in a different context above, as a researcher, you have to bet, right? As a researcher, you can't always say, you know what? All of our theories could be wrong. I'm going to distrust all of them and try to build up everything from the ground up. That's not really a way to get ahead, usually. So I'm glad that some people are thinking about alternatives to quantum mechanics, but there is literally zero empirical evidence that quantum mechanics is not right. And there are plenty of theoretical and philosophical and practical questions about quantum mechanics we don't know the answer to. So in my mind, the way more promising way forward is to try to understand the quantum mechanics we have rather than to try to throw it out and replace it with something else. Joshua Hillerup says, suppose a big expensive experiment is done in space, where according to general relativity, a small Kugelblitz is made, of a size where it should evaporate due to Hawking radiation in a reasonable time frame to observe for an experiment. A Kugelblitz is an idea of like a ball of radiation that you point into a small enough region to create a black hole. Assuming the experiment was performed correctly and there are no great advances in quantum gravity before then, would it be guaranteed to give us useful data, or could it potentially just confirm what is already known? We would certainly like to see up close the evaporation of a black hole and its final explosion, but there's no guarantee whatsoever that would give us useful data. So we have a prediction for what would happen. It would dissolve in a bunch of particles. It might be that more massive particles than we can create in current particle accelerators would be made, but they would be expected to very rapidly decay into other particles. So the whole point of Hawking's calculation is that what you expect to see coming out of a black hole is thermal radiation which has a more or less featureless black body spectrum. The one counterexample to this is if there are particles at very high energies, very high masses, which are stable or quasi-stable or long-lived enough that we could actually observe them, that would be wonderful new data. If there was something about quantum gravity that deviated from Hawking's calculation, of course, that would be wonderful, wonderful new data. But there's absolutely no guarantee that we would learn anything new. There very rarely are guarantees when you do physics experiments. Anton Grace says, I would like to ask you if you were always this open-minded, or if you had a different mentality in regards to the usefulness and purpose of philosophy in the past, and if so, what changed you? I don't think I was ever of the opinion that philosophy was useless. I just didn't know or think that much about philosophy when I was in high school. When I was an undergraduate and started to study it, I instantly thought it was fascinating and potentially important. I certainly went through a phase where I was one of these people who thought that all of the interesting questions of philosophy could sort of be tackled scientifically, right? Like right and wrong could be decided on purely rational, empirical, scientific bases. And I've changed my mind about that. I'm much more subjective about the notions of morality and ethics now than I used to be. Riverside says, would you agree that we are morally obliged to take preventative measures available to us in our present time to help avert or mitigate the terrible crimes that our future selves, persons branching out of us at each decoherence event, will commit against the future selves of our loved ones in some of the branching paths of the many worlds universe? So there's a couple of reasons that the answer here is no. One is, of course, the notion of moral obligation is a little fuzzy, and I generally don't like to use that notion in contentious issues. I mean, we might use it casually when we all agree on what the morality is. So in tricky questions, I like to be a little bit more careful than that. But more importantly, as I've already discussed earlier in the AMA, I think that the moral implications of many worlds are exactly the same as the moral implications of a version of quantum mechanics which was truly stochastic, in which there was only one world, but you just couldn't predict what would happen. I think that there are unlikely things that will happen, and there are likely things that would happen, and we should adjust our actions accordingly. I don't think that many worlds has any moral implications aside from regular quantum mechanics whatsoever. P. Walder says, in the recent episode of The Infinite Monkey Cage, you indicated that the many worlds interpretation naturally comes out of the equations of quantum mechanics. Jim Al-Khalili in the same episode indicated the many worlds view is not implied in the fundamental equations. Can you clarify for me whether it is or is not? So it depends on what you mean, okay? I hate to be weaselly about that, but you got to be honest. The equations of many worlds are just the Schrödinger equation and the wave function evolving. That's the fundamental definition of the theory. Unlike other versions of quantum mechanics, or unlike classical mechanics or something like that, the tricky part of many worlds is explaining why that theory accounts for the world we see, okay? Quantum mechanics, when we teach it in schools, that's when we use words like measurement and observation right there in the theory. So explaining the outcomes of measurement or observations is not hard because it's baked into the rules. In many worlds, there are no words about measurements or observations. There aren't even words about worlds or branching or decoherence. Those are all extra words that we human beings use as a convenient emergent way of talking about the wave function of the universe. So that's why there can be this disagreement about whether or not the many worlds theory comes out of the equations. The theory's equations are just the equations. There's no extra equations, there's no extra ingredients put on there, but there is extra philosophical work to be done to explain why that theory predicts the world that we see. Someone like me and many of the other people who've thought about this say, well, yes, it clearly does. There's clearly different parts of the wave function that don't interact and describe separate worlds, etc. Others do not see it that way. Judith Marsh says, whenever I see illustrations of black holes, they're always drawn like a whirlpool or funnel with things falling in the hole from the top. You can't approach it from the bottom. Would a real black hole's entire spherical surface send matter towards its center in all three dimensions? Do black holes have an equator? So I presume what you're thinking about are these sort of funnel-like diagrams where you see curved space-time and you sort of go down into the funnel. You know, let's be honest, these are picturesque representations that are trying to help you visualize something, and they're not very accurate. For one thing, they're not very accurate because black holes are regions of warped space-time, not just warped space. There's no up or down in space-time, but there is the future, and the point of a black hole is once you enter the event horizon, in the future of yourself, you will eventually hit the singularity. So do black holes have an equator? You know, it depends on whether the black hole is spinning or not. A black hole can be spinning, in which case it absolutely has an axis and an equator. A non-spinning black hole is perfectly spherically symmetric. So there's no difference in whatever direction you actually travel into it. Sam Hartzog says, my question is about gravity. The maxim for general relativity goes, space tells matter how to move, matter tells space how to curve. So is it more correct to imagine the force of gravity is acting on space-time itself, with the apparent action on matter being a byproduct of the spatial curvature imparted by gravity? I was thinking about gravitons when my mind went down this rabbit hole, so if you could give a little context on how gravitons might play into the answer, I give you 50 bonus points. So, you know, it's actually a slightly trickier question than you might even think, because when we teach general relativity, like if you buy my general relativity book and learn it from there, what you'll be taught is the following, that you solve Einstein's equations. Einstein's equations give you a consistent, simultaneous description of the energy generated by matter, what's called the energy momentum tensor, and the curvature of space-time, and it sets them equal to each other. But the geometry of space-time is described by what we call the metric, which tells you how space-time curves, is involved in both of those parts. It's involved in both the curvature of space-time, obviously, but also in the distribution of matter and energy through the universe. So you have to look for a simultaneous solution all at once. And then, once you do that, once you find a solution to the geometry of space-time, when you talk about, you know, how a planet goes around the sun or how a ray of light is deflected by the curvature of space-time, you idealize the planet or the photon as having no gravitational field itself. That's a little bit of an idealization, right? You're asking how a test particle would move through a curved space-time that it wasn't itself affecting. But in the real world, everything that has any energy whatsoever is going to both affect and be affected by the curvature of space-time around it. So it's not really that gravity is acting on space-time. I mean, gravity is a feature of space-time, but that feature is not separate from what the matter is doing. You have to sort of solve for both simultaneously at the same time. Gravitons play into the answer not at all unless you imagine quantizing gravity, and then it's exactly like electromagnetism and photons, right? You can talk about a classical electric field or magnetic field, or you could talk about them in photons, and there's a translation between the two, but if they're big in classical fields, there's no reason to talk about photons. Likewise, for big classical gravitational fields, there's no reason to talk about gravitons. Fred Alexander says, Scott Aronson stated on the Lex Friedman podcast that the greatest use of quantum computing will be studying quantum systems, thereby learning more about quantum mechanics. Do you agree? And if so, how and what might we learn? So I'm not sure what the greatest use of quantum mechanics is going to be. Studying quantum systems is absolutely one of the most obvious things you can do. It was the original motivation for people like Feynman in the early years of quantum computing. So clearly, a quantum computer is going to have an easier time simulating and therefore analyzing quantum systems than a classical computer will, just because of computational capacity. But I don't know whether that's going to be the killer app or not. I can imagine there's other apps that I haven't thought of yet. What are we going to learn about quantum mechanics? I don't think we will learn anything about the foundations of quantum mechanics, because I think the foundations of quantum mechanics are pretty much in place. I think what we'll learn is how the foundations play out, how the actual quantum interactions and entanglement and things like that arise and affect things in the real world where things are too hard to simulate on a classical computer. So we'll learn a lot about chemistry, for example. Chemistry at heart is all quantum mechanics, right? How different atoms trade electrons back and forth and so forth. That's all quantum mechanics, and we're not very good at approximating it. That's why chemists have a job and, mix chemicals in their labs. We can't really simulate it for any interestingly complex systems. So I think that we'll learn about how quantum mechanics manifests in the world, not about what the fundamental rules of quantum mechanics are. Alan Peterson says, a simple clarification question. How has the expansion of the universe changed over time? Did it start fast with inflation, slow down, and now accelerate? So this is a good question, actually, because it's tricky. What do you mean by the expansion of the universe? Here's how I would put it. The sensible way to quantify the expansion rate of the universe is through the Hubble parameter, right? We call it the Hubble constant, but of course it changes over time. And if you do it that way, the Hubble parameter only ever decreases throughout the history of the universe. As the universe expands, the Hubble parameter depends on the energy density, and the energy density ever only goes down until the cosmological constant kicks in and it begins to asymptote to a constant. So when we say the universe is accelerating, we don't really mean the expansion rate is speeding up. In particular, the Hubble constant is not speeding up during the expansion rate during the accelerating phase of the universe's history. Rather, what happens is individual galaxies, for which you say the velocity that you observe is their distance times the Hubble constant, that goes up with time because the Hubble constant becomes constant and their distance increases. So the apparent velocity goes up. If v equals h times d, velocity is Hubble constant times distance. In the ordinary way of thinking about things, the distance is increasing, but the Hubble constant is decreasing even faster. So the galaxy looks like it's decelerating away. But when the Hubble constant approaches a constant, the increasing distance leads to an increasing velocity, and that's what we characterize as the acceleration of the universe. It doesn't mean the expansion rate is going up. Nikos Tsagarakis. Sorry, I'm having a bad day today with the pronunciation of the names. I do apologize for that. But he says, Nikos is nice enough to say, do not worry if you cannot pronounce my name, just call me Tsagar. All right, Tsagar says, the thought is the following. Would a Laplace's demon need to be conscious at all? The Laplacian demon I'm talking about would not be a result of evolution, but would be an agent that was from the beginning on that level of computational capacity. So again, I think it depends on what do you really mean by Laplace's demon? So I could imagine a version of Laplace's demon that was conscious or one that was not conscious. So think of it this way. We think that our universe is big and there's all these particles in it and so forth. But what if we really do live in a simulation? What if we live in a simulation where the creatures that are simulating us are just enormously bigger and better than us in calculational capacity and power? So much so that to them, looking at literally everything in our observable universe is equivalent to us looking at a tic-tac-toe board. Okay, it might be hard to imagine that, but you can, in principle, imagine it's just a scaling, right? So to them, they're perfectly conscious, and as far as we're concerned, they're Laplace's demon, right? Like most of us don't have trouble imagining where the tic-tac-toe game is going to go soon, especially if it were a deterministic automaton rather than a game played by oppositional antagonistic opponents. So I can imagine a version of Laplace's demon that was perfectly conscious. On the other hand, I can also imagine a very minimal one that was more like just a computer, right? Like a computer that was simulating our universe with perfect fidelity. That kind of Laplace's demon wouldn't need to be conscious at all. So I think that the original thought experiment from Laplace just doesn't determine the answer to these questions, but you're very open, very willing, very able to think of different versions of it. Bram Blank says, I know that you know that evolution is a thing, and you've talked about the continuing evolution of the human race in some of your podcasts. I've always felt that we are actually de-evolving as a race due to medical science as well as societal pressures, making it possible for people to survive who would not have survived in the totally natural environment like the environment where humans first evolved. Do you think we are de-evolving, or are there offsetting pressures causing further evolution in a positive way? I think I would just unask this question, or at least I would deny the premises behind it. I think there's no such thing as de-evolution. I think that what seems to be implicit in the question you're asking is the idea that evolution, natural selection, right, in the Darwinian sense, is somehow progressive. It somehow makes us more and more powerful or intelligent or complicated or something like that. But there's absolutely nothing like that inherent in evolution. Evolution is not a story of progress. It's just a story of adaptation to a changing environment. And it's, slow, and there's a lot of randomness in it. But certainly in evolution all over the place, there are examples of capacities that species had being lost over time, right? There are species that used to have eyes that then burrowed underground and lost the ability to see, for example. It's still evolution. It's not de-evolution in any way. Their circumstances changed. Therefore, what kind of animal they were also changed. So I do think that evolution continues on, like it or not. We can tinker with our environment. We can even tinker with our genome at this point in time. But it is still true that sexual reproduction and mutation is going to lead to a slight set of changes in our genome over time, and they will be selected for. The pressures that select for different traits might be completely different in our current environment than they were 10,000 or 100,000 or a million years ago, but there still are pressures. Certain kind of genomes are going to give rise to more offspring than other kinds. That's just not going to stop happening. Gabor Peter Cesar says, it was good to see you in your office in the video of Veritasium YouTube channel. So for those of you who don't know, I recently appeared in a video on Veritasium where Derek Miller is trying to explain the many worlds interpretation of quantum mechanics, especially using the double slit and Schrodinger's cat and other classic experiments. So the question is, I saw there were some bottles on the shelves. Have you tasted any Hungarian wine? I recommend you the best sweet dessert wine of the world. It's Tokaji Aju. So I have tasted Tokaji. I'm a fan. I'm not a huge fan of dessert wines. I don't do them very often. More of a whiskey person if I'm going to have anything at all after the wine drinking portion of the meal has ended. But I have had it. It's good. I agree. I'm not going to agree that it's the best in the world because I have no opinion on that. I will not take sides on that issue. For those of you who are wondering, the bottles on the shelves in my office are champagne bottles, and they're all empty. There's one bottle for every PhD student I've had who has successfully defended their thesis. I think I'm up to 13 bottles right now, but it might be 14. I might be losing count. Okay, the last question is Ross Hastings says, my question this month relates to Donald Hoffman's fitness beats truth theorem and his claim that our perceptions of objective reality, including space-time, are a mere desktop interface, hiding a fundamentally different world altogether. What credence would you assign to the fitness beats truth theorem? So I think, I'm not that interested in this. I get a lot of questions about it. I don't think that there's a lot interesting going on here. There's a sense in which it is trivially true, and there's a sense in which I think it is deeply false. The sense in which I think it's trivially true is that, of course, our everyday picture of the world that we see with our eyeballs and touch with our hands doesn't give us very direct access to the true nature of reality, right? I think we all know that. If you think the true nature of reality, for example, is a quantum wave function obeying the Schrodinger equation, I don't see the wave function with my eyes. It's taken hundreds of years of science to figure that out. So we have other theories like Newtonian classical physics, or for that matter, Aristotelian physics, that are much more natural, direct, immediate models of the world around us. So in that sense, our perceptions are much closer to Aristotelian physics than they are to quantum mechanics, and therefore our perceptions are not giving us the entire truth. I think that's kind of obviously true, and I'm not surprised by that. But the idea that we somehow can't get to the fundamental reality underneath it all, or the idea that there isn't any fundamental reality, or the idea that we are creating a fundamental reality, or the idea that different people have different versions of fundamental reality, or there is no fundamental reality. I don't like any of those ideas at all. I think there is a fundamental reality. I think we're getting closer and closer to it. I think the process by which we get closer and closer to it is called science. This is what I do for a living. I think that, there's a school of thought, which I think that Hoffman is sympathetic to, although I don't know whether he would characterize himself this way. But there's been a school of thought for hundreds of years that puts mental action at the center of things and physical reality as a subsidiary or secondary thing, right? There's different, I'm being intentionally vague because there's different variations on this theme. But idealism and other theories that put mind at the center and physical reality secondary. And I am entirely on the other side of that. I think that physical reality comes first. Mind and cognition and thinking and perception and so forth. These are all just ways of talking about certain aspects of objective physical reality. And if you want more on that, you can buy my book, The Big Picture. Very glad that I've written all these books now so I can actually tell people to go read them when these questions come up. But okay, that's it for this month. Thanks very much for listening in. And those of you who are here first because you're not Patreon supporters, I hope you enjoyed it. I hope you got something out of it. Come back next month when we'll have another exciting bout of questions here on Mindscape AMA.